Since we ended up talking about the electrical domain last time, I'm not going to go into the details of that now. Let's just start talking about the scaling advantage. Okay. One of you guys mentioned this today, the scaling advantages of electrostatic forces. So at the microscale, electrical forces can be used to move objects, and this has been used in a lot of different devices, which we'll talk about. This can be used using simple scaling arguments. So if we were to take the two metal plates and place them next to each other, what type of device is that? A capacitor, right? Two metal plates with a dielectric material in between. Okay, dielectric material is an insulating material. Okay. Now, you can make capacitors with air in between. If you take two metal plates and you have air in between them, that's also a capacitor. Okay. And you can apply all the standard capacitor analysis equations and derive, if you can actually derive the electrostatic force balance, the electrostatic force generated between those two capacitor plates. The reason why that happens is that, let's say you take two capacitor plates like this and you put a voltage source across there. You have a buildup of positive charge on one half of the plate, and then you have a buildup of negative charge on the other half. This is, oops. Let me fix this here. Oh, wait. This is not positive charge, it should be negative charge. All right, so if you have two opposite charges attract each other, right? So the thing is, these charges are stuck in the metal. Okay, they can't go through the air. The air is an insulating material, so the charges are really stuck here. And so what those charges do, they build up. There's an electric force that builds up between them. You can derive what the force is using just a basic electromagnetic theory, and that force will cause the two plates to come towards each other. Okay, the electric force is equal to 1/2 times epsilon. This is the dielectric constant. So this is the dielectric constant of air. V squared is the V is the voltage being applied between the two plates. L, W, and D. The L and W are the length and width of the plates. D is the distance between the two plates. All right. So as we scale down the system, the interesting thing that happens is that, let's say if we were to compare that with the gravitational force, the weight of the electrode. Okay. The thought experiment we're doing right here is, let's say we want to get a metal plate to float. Could we use electrostatic forces to actually levitate a plate? Okay. If we were to do something like that, the analysis that we would do in our head is that we want the electrostatic force that's holding the metal plate up to be the same as the gravitational force that would pull it down. Okay. Now, in reality, I should note that these types of electrostatic forces are never repulsive. They're always attractive. You put a voltage between the two plates, you get opposite charge on either sides of the plate. You only get attractive forces. We're doing this thought experiment just so you can see the ratio of the forces. Okay? The gravitational force, the weight of the electrode, that scales as length cubed. So if we look at the gravitational force, if we look at the, this should be the electric force divided by the gravitational force. Sorry for this mistake here. So if we look at the electric force divided by the gravitational force, we find that it's V squared over epsilon divided by length cubed. So what this means is that this scales as length cubed. So even at a 10 times smaller length scale, the electrical forces compared to the weight of an object becomes 1,000 times more significant, 10 to the third times more significant. Okay. Now, this doesn't mean, in reality, we're not levitating objects. What it means is that we can actually move objects. We can move objects with electrostatic forces, and we can't do that at the larger scale. The way this is used, a very good application of this is in what's called digital micromirror devices. Have any of you seen these types of devices before? Have any of you heard of this, the DLP? Let's take a look at this one real quick. So this is digital light projection technology. May as well just watch this video. It's just a few minutes. I think you'll find it interesting. DLP is made up of electrostatic mirrors.
Hi, my name is Dylan Thomas with Texas Instruments DLP. DLP is one of the most flexible semiconductors in use today. You'll find it in projection systems ranging from cinema projectors all the way down to cell phones. However, many developers are also using this amazing technology in new applications, ranging from measuring and sensing to digital exposure to intelligent illumination and even wavelength control. DLP can be used with many different light sources, ranging from lamps to LEDs, also known as the DMD.
All right, this is a micromirror
DMD
device.
is a MEMS device that belongs to a class of optical MEMS known as spatial light modulators. When combined with optics and light sources, a spatial light modulator allows users to program high-speed, very efficient patterns of light. Each DMD consists of an array of hundreds of thousands to even millions of tiny micromirrors.
These are all micromirrors.
Each of these micromirrors is on the order of about 10 microns in size. That's 1/10 the size of a human hair. The DMD is created using TI's proven semiconductor manufacturing processes. TI has delivered over 40 million DMDs since 1996. Each micromirror consists of a CMOS memory cell, upon which the reflective aluminum micromirror structure is built. The micromirror, or pixel, is highly efficient at reflecting UV, visible, and infrared light. The micromirror is a digital two-state device that can be operated at either plus 12 degrees or minus 12 degrees.
Okay, do you
During
see how that's...
operation, a 1 or a 0 will be loaded into the memory cell for each micromirror, which allows independent control of each pixel.
These micromirrors are electrostatically moved, electrostatically actuated.
To either a plus 12 degree state for a 1 or a minus 12 degree state for a 0. In a typical setup, the light sources, which could be an LED, a laser, or a lamp, will illuminate the DMD at an angle of 24 degrees. Each pixel then directs light to one of the two output ports. The DMD is capable of displaying patterns at speeds up to tens of kilohertz, making it one of the fastest spatial light modulators available. TI has a broad portfolio of DLP micromirror arrays to meet your needs, ranging from a wide...
All right, so the idea here is that these mirrors, these micromirrors, can actually be switched from one state to the other, meaning like at this angle or at this angle. The angle that they switch is about 12 degrees, plus or minus 12 degrees. The way that they move is through electrostatic actuation. So on this side of the plate, they'll have a capacitor on one side, they'll have a capacitor on the other side, essentially. Now, let me just draw this out. I think this will be easier to see. Okay, so the digital micromirror device takes advantage of electrostatic forces. The basic model for this looks something like this. You have a capacitor. Well, you actually have two capacitors. Okay, I didn't do a very good job of drawing that. Okay. There's a metal plate here. It's attached to a region where it can rotate. Okay, the mechanical diagram might look something like this. If we were to apply a voltage here between these two sides, you will get positive charge buildup across the entire plate here. You'll get negative charge buildup here. Actually, most of your positive charge will be built up on this side of the plate, you'll get an electrostatic force on this side. And that will cause the micromirror to rotate in one direction. And if you apply the voltage on the opposite side, then it will rotate in the opposite direction. Okay? This is taking advantage of the scaling because electrostatic forces are very reliable force actuators, and they're very quick. Whenever you apply the voltage, the thing will move within tens of milliseconds, or even less, I think. Okay, so they're taking advantage of the scaling, and this is one of the most successful MEMS devices on the market. It has revenues over. You can see that the sales in 2011 was $2.5 billion, 20% of Texas Instruments' revenue. Does anyone know where digital micromirror devices are used? The developer guy was telling you there's a lot of different applications, but do you know what the main application is? TVs. Well, not TVs anymore, but movie theaters. You have these projection systems. The movie that we were showing, they said that you have a light source coming in this way, right? This is a lamp. This comes into your micromirror device. Now the micromirror device, each of the mirrors in there can have two possible angles, right? And this is the output. Okay, so this is the front of the projector. If the angle of a mirror is at one state, then the light from the lamp will come in and it'll go through this projection lens and it'll go to the movie screen. If it's in the opposite state, then the light will get reflected away and it won't go to the projection screen. Right? So each one of these mirrors is one pixel in your movie. Right? So if you have a 1080p if you have a 1080p image, that's like 1920 pixels by 1080 pixels. Texas Instruments actually has, so they have micromirror devices that actually have 1980 multiplied by 1080 mirrors on a single device. They're not cheap, but they have them. Okay, so the advantage is that you can cram a whole bunch of these mirrors into a small device, and because the devices are small, they're small enough to be actuated by electrostatic forces. Now in the movie you also saw that each one, under each one of these devices there's a CMOS memory cell. So all the circuitry that controls the voltage between one side of the pixel and the other, each one of those pixels also has circuitry embedded underneath it. Right, so it really is quite an amazing device. There's electronics embedded underneath, and then the layer on top of it consists of those micromirror devices which can rotate between two possible states. So there's two scaling advantages of this. The first one was the electrostatic forces. The second one is the speed. The smaller your device, the quicker those devices can move. All right. If you don't mind, I'm just going to finish up the electronics section. That'll just take a couple minutes here. The next thing I want to talk about here is Moore's Law. Okay. Another very big thing in the miniaturization in the electrical domain is a miniaturization of transistors. Okay, with Moore's Law, some of you have probably heard of Moore's Law before. It's the shrinking of the electrical transistor. The transistor is a basic building block for microprocessors. A microprocessor is made up of over 1 billion transistors. Now, what's happened over the last 30 years is that the transistors have gotten smaller, and we can cram more and more transistors on a single chip. If you look at back in the 1970s, the first microprocessor that Intel sold, 1971, it had probably a few thousand transistors on it. The size of the transistor was 10 micrometers, and it operated at tens of kilohertz speed. We're talking about the CPU clock rates. Now, we have more than 1 billion transistors on a chip. You can see that the number of transistors on an integrated circuit has gone up quite rapidly. This was in 2004. By now, 2015, we're over 1 billion transistors on a chip. This is a 2012 microprocessor. When you make the transistors smaller, you have a smaller transit time. This is proportional to L. You have a lower parasitic capacitance because this is proportional to L squared. You have lower energy consumption per transistor. This is also proportional to L squared. And you can cram more and more transistors on a single chip. Because we've been able to manufacture the transistors smaller and smaller, we've been able to take advantage of a lot of these things and get huge performance benefits. When you make the transistor smaller, when you have a smaller transit time, when you have smaller parasitic capacitances, you can operate the CPU at a larger clock rate. So the 1970s microprocessor was operating at tens of kilohertz. Nowadays, microprocessors are operating at what, like 3 gigahertz? Right? We're talking about the clock speed on the microprocessor. When you make when you reduce the parasitic capacitances, the microprocessors, the transistors can switch between the on state and the off state very, very rapidly. Okay, for those of you who aren't electrical engineers, it's okay that you don't understand all the details of this, but just what we're doing right now is we're looking at the scaling. So when you make the transistors smaller, they become 4,000 times faster, 5,000 times less energy consumption per transistor. However, I should note that since there are more transistors on a chip, the overall power consumption of a microprocessor has gone up. Let me repeat that. The energy per transistor has gone down by a factor of 5,000, but because we have so many more transistors on a chip, we're still consuming more power. So this is an issue why microprocessors are, heat dissipation is a big problem in microprocessors now. It's 50,000 times cheaper, so this is an economic benefit. This comes from the fact that you can make the transistors smaller and smaller. All right, so there's so many reasons why you'd want to miniaturize a transistor, and this is really what's been driving the electronics industry for the last 30 years or so. Just make those transistors smaller and smaller and smaller, and you get these huge performance benefits. Gordon Moore, the guy who founded Intel Corporation, he predicted that the numbers of transistors would double every 18 months, every year and a half. That didn't quite happen, but they ended up doubling every 24 months instead. So his prediction back in the 1970s held quite true over 30 years. It's quite amazing. It's one of the greatest predictions in the semiconductor industry, in any industry really. He predicted that our manufacturing technologies would get better to the point where we would be able to double the number of transistors on a chip every 18 months. And he was pretty close. Now what's happened is they've made the transistors so small now that it's hard to make them any smaller. They're almost at atomic scales right now. Okay, if you look at the R&D pipeline right now, transistors in production right now as of 2011 were 22 nanometers. Now they're down to 14 and 10 nanometer processes. Eventually they're going to try to get down to 7 and 5 nanometers. At these length scales, the physics changes again, because the physics that they designed for working at the micrometer to nanometer length scale, or to the submicrometer length scale, micrometer to submicrometer length scale, that's what the transistors used to be. Now they're getting down to nanometer length scales, and we're starting to see other physical effects happening. So now they're trying to fundamentally redesign the transistors to continue giving performance benefits. They've thought about going away from silicon to other materials. They've thought about using things like carbon nanotubes, single electron transistors. They've thought about spintronics, different physics. People are exploring different physics to continue this demand for high-speed electronics that we all, that we've all built up over the years. So we'll end with that here. We'll start talking about the fluid mechanics domain in Friday's class. Okay, so these were some of the domains that we covered, or that we will be covering today. Now, are you all starting to see some of the similarities between the different domains? If you haven't yet, and hopefully by today you'll have a sense of that. We covered the electrical domain last lecture, and this lecture we're going to talk about the fluid flow domain. We're going to talk about the thermal domain. And we'll also talk about the mechanics domain. Okay, each one of these domains can be modeled by equivalent circuit models. So one of the things that we're going to talk about today is how to model different systems using equivalent circuits, electrical circuits, like resistors, capacitors, voltage sources, and current sources. Okay. For those of us who are electrical engineers, we've all analyzed circuits in that manner. And that allows us to find the voltages and currents at specific nodes, right? Well, it turns out that you can use the same circuits, or you can use similar circuit models to analyze fluid flow. You can use the same circuit models to analyze heat flow, and you can even do things like rigid body mechanics, and also species transport, like diffusion and things like that. So it's actually quite helpful to be able to model systems like that. So we're going to be doing some very basic modeling just to give you a flavor for how you can analyze microsystems in various domains. So I mentioned last time about the flow analogies between charged fluid and heat. Electrical current flows from high voltage to low voltage. Fluid flows from high pressure to low pressure. And then heat is transferred from high temperature to low temperature. And in the electrical system, we have a wire that has some type of electrical conductivity. The charges are flowing from one place to another. In the fluid flow domain, we have a pipe will have a fluidic resistance or a hydraulic resistance. That so when you put a pressure from one side of the pipe to the other, the fluid flows from one side to the other. And in the case of heat transfer, you have a material that has a certain thermal conductivity, and heat flows from one place to another in the thermal domain. There's also concepts of capacitance in each one of the domains. Capacitance being a unit for a way to model energy storage. In the electrical domain, capacitance is a device that stores charge. Stored charge is stored electrical energy, like a battery. Okay, so capacitor stores charge. In the case of a fluid, you can store fluidic energy, so to speak, by having a container that expands like a balloon. Okay, when that container expands, it holds some elastic energy, and that elastic energy can then recompress to release the fluid flow and create a pressure gradient. In the heat transfer domain, when you heat up an object, that has a thermal capacitance. So when you heat up an object, that object is storing thermal energy, right? And then when that is connected to, when that is connected to some sort of a body that can transmit heat, the heat can be transmitted from that body to another body. Okay, so there are flow analogies in the electrical, fluid, and the heat transfer domain. Last time we started off by talking about the electrical domain, and since we're also talking about scaling advantages, we talked about one of the big scaling advantages in the electrical domain, and that was electrostatic forces. Basically, we found that the electrostatic forces become the electrical force scales as 1 over the distance between the two plates squared. Okay, so as the distance between the plates becomes small in microsystems, the electrostatic force starts to go up very rapidly. When you get down to the small domain, this electrostatic force is actually enough to move things. It's enough to move metal plates. If you consider the mass, not even necessarily the gravity, but just the mass of an electrode. At the large scale, that doesn't happen. At the large scale, you cannot move a large mass with electrostatic forces. But at the small scale, the mass of the electrode scales as length cubed, and the electric force scales as 1 over length squared. So you end up getting a lot more. The ratio of electric force divided by the mass of the object, the weight of the object, it becomes very significant. So the example that we ended off with last time is that we saw that a digital micromirror device, which is one of the most successful devices made by Texas Instruments right now, it accounts for 20% of their revenue as of 2011, is a digital micromirror device where you have a bunch of mirrors that are electrostatically actuated. The mirror can tilt in one direction or the other using electrostatic forces. There can be millions of them on an array, as we saw in the video last time, and these are used in digital projection systems, in digital movie systems. So if you go to Star Theater and watch a high-definition movie in their digital projection system theaters, they actually use DLP devices. These are called, here it says in the slide, DMD, digital micromirror devices. Texas Instruments markets these things as digital light projection devices. Okay, and they're not just used for movies, but they're actually used in certain types of biomedical applications as well. This was an example of where the micromirror device was actually used to make oligonucleotide microarrays. So DNA microarrays. It was used to, as a part of the process of making this microarray, you actually have to shine light in specific spatial patterns onto the substrate. It's a light-activated chemical reaction, right? And in each one of these spots, they were actually able to grow a different nucleotide, okay, a different DNA sequence, and that's a very important step in making DNA microarrays. So they actually, DLPs actually have use in biotechnology as well. And then we ended off the class talking about the miniaturization of transistors. All right, this is another thing where you can analyze, you can use scaling laws to analyze some of the trends that are happening in transistors. The basic thing that we said was we've made the transistors smaller. As the transistors have gotten smaller, we're able to cram more transistors on a chip. So each transistor consumes less energy, but since there are more transistors on a chip, the overall power consumption is much higher. You're generating heat at a much higher rate. Okay. The size of the chip has remained the same. The size of the transistor has gotten smaller. Because of this type of scaling, the heat generation in microchips has gotten much more severe. Transistors have become faster. These chips have gotten a lot faster, but the heat consumption is becoming more of a problem now. So I won't go over this again. You can look over the last lecture. We talked about the different aspects of how the transistor scales. This is in the electrical domain. So now we're going to start off by talking about the fluid mechanics domain. And again, like I said with the electrical domain, I mean, we could spend an entire semester talking about just the basics of fluid mechanics. I'm just putting a few basic concepts in here to give you a flavor for what this domain is about and how it's related to the other domains. In fluid mechanics, we're considered, or in the microfluidics area, we're often concerned with how fluid flows through a microfluidic channel. Okay, and this is not that much different than how electrical current flows through a wire. Okay, for those of you who are mechanical engineers, this is going to appear quite simple. So please do bear with me. For those of you who are not, then hopefully this will be a very brief but a good introduction to it. A few essential concepts. In the fluid mechanics domain, we are interested in finding the velocity of fluid as it flows through a channel. We are interested in calculating the volumetric flow rate. And often we're also interested in calculating the pressure. As I mentioned, if you put, when you flow fluid through a channel, one side of the pressure is at a higher pressure than the other side. Okay, it's like how a voltage drop develops when you push current through a resistor. Okay, just like you can design pretty complex circuits, with microfluidics you can design very complex fluidic networks of channels. Okay, and we're often interested in analyzing how fluid will flow through those through those channels. Properties that we're interested in: the density of the fluid and the viscosity of the fluid flowing through the channel. Those are the things we're often most interested in. The next point here, incompressible flow applies to most liquids. In fluid flow, we talk about compressible and incompressible flow. Okay, compressible flow is when you're flowing a gas through a channel. Okay, gases are compressible, right? When compressible fluids flow through a channel, the analysis is a little bit more complex than when incompressible liquids flow through there. Because if a gas flows through a channel, a gas pressure can build up in a certain location in the channel. If you were to flow gas into a channel that has no opening, you'd still be able to flow gas in there. The pressure inside the chamber would just build up. Right? Compare that to if you have a channel filled with liquid. Once the channel is filled with liquid, you can't put any more liquid in there, right? So the fluid flow equations in compressible flow have to deal with the fact that the pressure can change. when we're dealing with liquids, which are generally considered to be incompressible. You can't compress liquids, right? In those types of situations, the flow equations become a little simpler. All right. So incompressible flow applies to liquids, and what this means is this del dot u. This is called the material derivative of the velocity, and this is equal to 0 in the case of incompressible flow. Okay, we're going to be dealing primarily with incompressible flow. Another important concept here is what's called the no-slip boundary condition. Let's zoom in on this here. So let's take a basic situation where we have fluid flow through a microfluidic channel. Okay. The no-slip boundary condition states that the velocity at the wall is 0. Okay. Now, if you think about this, this should make sense because you have friction at the wall, right? The wall is not moving. The velocity of the wall is 0, right? So if the velocity of the wall is 0, then the velocity of the fluid, which is right at the wall, also has to be 0. Right? Because the two are in contact with one another. At the wall, the flow velocity is 0. This is an example of what's a flow profile. What happens? If you were to flow, let's say at the bottom here, this is the distance from the wall, y, and this is the velocity, we'll call that u, right? So this is a situation where we have fluid that's just flowing through, let's say, it's flowing through a channel, and this represents the bottom of the channel, okay? And this side could be free, let's say. This is called Couette flow, by the way. C-O-U-E-T-T-E. This is where you have one wall and the other side is free. These vectors are showing what the fluid velocity is going to be like. Notice that the fluid velocity at the wall goes to 0. This is what the no-slip boundary condition represents. The flow velocity at the wall is 0, and you can see that the velocity increases as we go further and further away from the wall. This is what's called a flow profile. So from this arises the shear stress. This is the next concept. So within this flow profile, if we were to plot this velocity as we have, notice that the velocity looks like a curved function. It's 0 here, and it increases, and then it starts to level off once we get to the farther away we get from the wall. So this is a curve, right? The curve has some sort of slope associated with it. From the slope of this curve, du dy, we can calculate something called the shear stress. All right. Does anyone know what shear stress is? How do we define shear stress? How do we define normal stress? Pushing down. Right. Let's just show this real quick. Okay. So this is the typical picture that's used to describe normal and shear stress. So normal stress would be stress that's applied directly orthogonal to a surface. orthogonal So if we were to apply pressure or normal stress, which is orthogonal to a surface, this would cause the shape to deform this way. Now shear stress is applied parallel to the surface. So if we were to apply a force this way, so you take two things and you're shearing it like this. On the opposite side, you're applying the opposite force. Then this is going to cause this shape to become, instead of a square, it's going to become more of a, it's going to deform in this manner. So shear stress is parallel to the surface. We'll talk more about this later. So shear stress is, you can think about friction as shear stress, okay? This is sort of a frictional force. Now, if we looked at this last thing, and if we consider, I don't know if you remember or not, like a couple of classes ago, when we're dealing with the fluid domain, we think about the elementary particle as a packet of fluid. Okay, in the electrical domain, we consider an elementary particle is a charge, right? Moving charge is current. In the fluid domain, we consider a small packet of fluid, like 1 cube of fluid, for example. That's the unit quantity. Okay, so this unit quantity actually gets the shear stress is talking about how this a packet of fluid experiences stress. Okay, normal stress is the pressure that's pushing this packet from one side of the channel to the other. Shear stress is this frictional force due to this velocity gradient. Okay, the sharper the velocity gradient, the more the shear stress. Now, think about this. Compare the flow in a large pipe. Compare that to the flow in a very small pipe. What is the difference here? In terms of shear stress, which one do you think is going to have more shear stress?
Small pipe.
Small pipe. Why would the small pipe have more shear stress?
It's more interaction with the outside of the pipe, but inside the pipe.
Absolutely. That's exactly right. It's closer to the wall. Okay, in a small pipe, you're always closer to the wall, right? So you have more interactions with the wall. These velocity gradients always arise near the wall. And so the shear stresses arise near the wall. So this is one of the reasons you end up having more shear stresses in a microfluidic device than you would have in a large-scale device. All right, and if you know what the velocity profile is, it's very easy to calculate the shear stress. The definition of shear stress is the velocity gradient, okay, so the slope of this curve. If we were to draw the velocity profiles like this and draw a curve next to it, du dy multiplied by mu. And the mu is the viscosity of the liquid. The more viscous the liquid is, the more shear stress you're going to have. Okay, this is also the definition of viscosity. Since we were talking about the different material properties, viscosity is a very important property for liquids. So something thick like honey would have a high viscosity. viscosity of water would be comparatively less. All right. So let's move on here then. When we analyze flow through a channel, we can use what's called the Navier-Stokes equations. This is a fundamental equation similar to, analogous to like Newton's laws of mechanics, although this arises from Newton's laws of mechanics. But this is one of the fundamental equations used to analyze flow in a microchannel. All right, the Navier-Stokes equations for single-phase incompressible Newtonian flow is as follows down here. Okay, the reason why I've included just this equation is because with microfluidics, this is generally what we are concerned with. There are more complex equations for compressible flow, and also if you have non-Newtonian flow, then also the equations change. By the way, Newtonian liquids. All right, you may have heard this term Newtonian versus non-Newtonian liquids. In a Newtonian liquid, the viscosity of the liquid remains fixed. Okay. In non-Newtonian liquids, the viscosity of the liquid can actually change depending on how much shear stress that you put on it. Okay. So going back to this mu would be a constant in a Newtonian liquid. All right. Examples of Newtonian liquids, well, most liquids, like water, for example, would be considered a Newtonian liquid if you have something like something like blood that has sort of a suspension of particles that can behave as a non-Newtonian fluid. So that's something you have to think about. All right. But engineers often like to simplify, and we simplify it using the assuming Newtonian flow, assuming incompressible flow. In a lot of cases, this analysis will work, or at least it will give us a first-order approximation of what is happening inside the microchannel. All right, another very important simplification is this concept of low Reynolds number flow. All right, if we look at the Navier-Stokes equations, it's a partial differential equation, rho du dt. All right, u is the velocity, rho is the density. And then we also have this u dot del times u. So this is what's called a material derivative term here. Okay. On the right side, we have this delta P, a pressure term. Next to that, we have a viscous term, mu del squared u. And then we have a body force term. Right. So the Navier-Stokes equations is sort of it's a statement of a conservation of it's balancing forces, and it's also balancing momentum. All right. There are different force terms in here: body force, viscous force, pressure force. And on the left side here, this is what's called the inertial force. Now, inertial force, remember, inertia, momentum, force is equal to mass times the velocity. All right. These terms have to do with the density of the liquid. So the density of the liquid is related to its mass, rho times u. And we also have another rho and a u term here. These are what's called the inertial terms. Now, if you are in what's called low Reynolds number flow, then these terms become insignificant compared to these terms. All right, and it turns out this simplifies the system hugely. Okay, because you don't have this material derivative term to deal with. You don't have this other term, this time derivative, to deal with also. So in terms of analysis, it takes out the two most complicated parts of that partial differential equation. All right, it makes flow very easy to analyze in a microfluidic device. And it turns out it also makes the flows much more predictable. All right. So what does it mean to operate at low Reynolds number? We've been doing scaling analysis, so this should start to make sense now. Remember when we were talking about the electrical domain, we said, well, we were comparing the force, the electrical force, compared to the gravitational force, right? We did the ratio of the two. Okay. The Reynolds number is a statement, is a fraction that says it's a ratio of the viscous forces, it's the ratio of the inertial forces on a packet of fluid divided by the viscous forces on that packet of fluid. All right? So, if you were to go through that analysis and simplify it, you'll see that the Reynolds number comes down to rho times U times L divided by mu. Okay, let's talk about what these terms are. Rho is the density, U is the velocity of the liquid, L is the length scale. Okay, notice that there's a geometric parameter here. So the length scale is the dimension of the channel, one of the dimensions of the channel. In the case of, just a circular microchannel, it's the diameter of the channel. Okay. In a square microchannel, it's similar. Like the typical length scale is would be a dimension of the channel. On the bottom here we have mu. Right. So how does this scale to the microscale? This is a function of L. All right. So in a microfluidic device, the Reynolds number drops precipitously. Not only does L go down, but you can imagine that in a really tiny channel, the velocity of the liquid in the channel is going to be smaller than if you had a very large pipe, right? So it turns out that this U term also goes down. So if you just consider L, then the Reynolds number scales as just the length. If you consider that the U is also going to go down, the velocity is also going to go down as you shrink down the system, then it becomes proportional to L squared. So in a microfluidic device, you're always going to end up having low Reynolds number flow. I shouldn't say always, because there are some folks who are using high Reynolds number flow in a microfluidic channel they drive the fluid through there very, very fast. In that case, you can get slightly higher Reynolds number. But often in many microfluidic devices that we're going to see, the Reynolds number is much less than 1. All right. The Reynolds number is a dimensionless number, and folks who are mechanical engineers, thermal engineers, fluids engineers, they use dimensionless numbers a lot. Dimensionless numbers generally describe the relative effect of one phenomena versus another phenomena. So the fact that this is less than 1, okay, if the fraction is less than 1, that means that the viscous forces, the inertial forces are less than the viscous forces. All right. In the Navier-Stokes equation, that means these terms become insignificant compared to these terms. If you look at the right-hand side of the equation, this is a much simpler equation to analyze. In fact, these equations look very much like the equations for describing current flow in response to a voltage being placed across a resistor. It's the same idea. So it turns out you can model microfluidic systems in the same manner. So at low Reynolds number, the inertial term disappears, resulting in laminar flow. And you can solve the Navier-Stokes equations, the simplified Navier-Stokes equation, using you can actually solve this by hand, but you can also do simulations of it, and you can figure out the flow profile. All right. Now, this is one thing that is different from the electrical domain. So those of us who are coming from electrical engineering, when we're analyzing fluid flow in a pipe, we have to consider that we have a velocity profile in there. So this has to do with what I just mentioned about the shear stress. In the walls of the pipe. So now imagine that we just have a pipe like this, and we're flowing fluid through there. Near the walls, the velocity of the fluid is going to be 0 because of that no-slip boundary condition. So it's 0 up here, it's 0 down here. The fluid flow is going to reach a maximum in the center of the pipe. Right? This is you think about this as sort of intuitive. You can actually solve for this velocity profile by using the Navier-Stokes equation. You solve the Navier-Stokes equation under certain boundary conditions. Okay, this is a partial differential equation. If you want to solve that, you need to put in boundary conditions. So the boundary conditions would be this no-slip condition. We say that the velocity u is 0 here, and it's 0 here. We also assume that we've applied a pressure gradient through the pipe, meaning we have a high pressure on this side, low pressure on this side. So that gives us our delta P. And then if we have any body forces exerted in the liquid, we include those. In basic fluid flow through a pipe, there's no body forces. Okay, we can ignore gravity, especially in microfluidic devices. All right. If we were to solve that partial differential equation, we would find these relationships. Delta P is equal to Q times RH. This is an equation that's very similar to Ohm's law, V equals IR. The delta V across a resistor is equal to the current times the resistance of the resistor. In the case of fluid flow through a pipe, the delta P, the pressure gradient, the difference in pressure between one side and the other side, is equal to the flow rate, volumetric flow rate times the hydraulic resistance. And the hydraulic resistance is 8 times mu times L divided by pi r to the fourth. So we have the length here, and then on the denominator we have r to the fourth. So the hydraulic resistance is very dependent on the radius of the pipe. So this is r to the fourth. Okay? So what this means is that the hydraulic resistance of a microfluidic channel goes up very dramatically at the microscale, to the point where you actually need large amounts of pressure to drive fluid through there. This could be considered one of the disadvantages of microfluidic systems, is that you do need, large amounts of pressure to drive fluid through a channel. Okay, so if we want to drive, if we want to pump liquid through a microfluidic channel, there may be other pumping techniques we can use besides traditional pressure-driven flow that can be more efficient, so to speak. Okay. This equation describes the velocity profile as a function of r, okay, the radius. Okay. This is flow through a circular pipe. So the flow through a circular pipe depends on the radius. You can see that in this equation, the maximum velocity will happen when r equals 0, so when you're at the center of the pipe. This term goes away and you reach a maximum velocity of 1 over 4 mu delta P delta X divided by r squared. Right, this delta P delta X is the pressure gradient. What else can we say about that? If you were to integrate this this velocity, if you integrate this velocity over the cross-sectional area of the pipe, then you'll get the flow rate, or the flux, and then you can calculate the volumetric flow rate from there. Let's see if this link works. So I wanted to show you this page also. I've been showing you a lot of these pages from Hyperphysics, just because I'm a fan of this website. It just has a lot of essential fluids concepts. Okay, if you're intimidated by, if you're seeing this for the first time and it seems intimidating to you, you can just look through this website and you'll see all the basic concepts, and you'll probably recall a lot of these from your physics classes before. Okay. Things like the fluid friction. This is what ultimately causes shear stress and the viscosity. There's static fluid pressure, hydraulic pressure, hydrostatic pressure. All these different effects here you can sort of read through in Hyperphysics. So we can talk about one scaling advantage in microfluidic devices. In fact, we've already talked about this before. The Reynolds number. Okay, at the small length scale, the Reynolds number becomes small. Often it's less than 1. The Reynolds number represents the ratio of inertial force divided by viscous force. When inertial forces are small, you end up getting something called laminar flow. Okay. Laminar flow looks like this. I just showed you on the previous slide. You have nice, well-defined velocity profiles that do not change with time. At high Reynolds number, you can start to see unsteady flows. Unsteady flows means flows that do change with time. And often the fluid will actually turn into these rotational features called vortices. Those vortices can change with time, and they make analysis of the fluid flow more challenging. We've all experienced turbulence when we're on a plane. Pilot says, we're experiencing some turbulence. What's happening is there are these microvortices forming underneath the wing of the plane, and that's causing the plane to sort of like bump up and down. All right. If you've seen like flow of water past a rock, you'll sometimes see patterns that look like this. Let me give you one example here. This is another classic schematic that's shown for laminar, for describing laminar versus turbulent flow. This is a nice example because it just describes the concept well. Let's say you have a static object, a rock, and there's fluid going past there. At low Reynolds number, the fluid flow will look like this. The flow vectors. All right. So this could be a stream, and this could be a rock sitting in the stream. Another thing you could imagine, if this was the wing of your aircraft, this could represent the flow of air across the wings of the aircraft. So this would be considered laminar. Turbulent flow would be something like this. Where you end up getting these vortices that are forming this is sometimes called vortices. And these vortices could be unsteady in time. They form at different locations, they come and go. All right, so the difference between here is this upper example is that it's a lower Reynolds number flow. The upper example is it's laminar flow, and below is what's called turbulent flow. Okay. In microfluidic devices, we generally will see laminar flow. We're at low Reynolds number, and you end up seeing these types of patterns. Okay, turbulent flow is a little bit more difficult to analyze. So in microfluidic channels, we exploit low Reynolds number flow and the unique properties of laminar flow. Laminar flows are very predictable, and they're easy to model using simple circuits. We'll see an example of that on the next slide. As an example, in laminar flows, two streams will continue to flow parallel to one another. Because you see how these flow vectors are all running parallel to one another? Because of that, if you were to combine two streams, as we've done in this example here, there are, for example, here you're combining 5 different streams together, and as you can see in this example, the 5 streams flow parallel to one another. This is another example of that, where you have 6 different streams, and these 6 different streams are being combined into a single channel, and you can see that the fluid flows parallel to each other. Okay. Eventually what will happen is that these colors will actually mix with one another, but that mixing is happening by diffusion. Okay, like the molecules here will actually end up diffusing over this way, and vice versa. So eventually these gradients will go away, but the flow is still the same. The flow is always happening parallel to one another. Very predictable, very easy to do. If you wanted to get this to happen in a larger pipe, you would have to flow liquid through the pipe at a very low velocity, relatively speaking. Generally, with fluid flow through a large pipe, you end up getting turbulence, and the liquids mix on each other. They turn around each other, so the fluids mixing is enhanced. You can imagine that if you have flow patterns that look like this, that's essentially mixing the fluids, right? So one of the nice features about laminar flow is that you can get very well-defined gradients of chemicals by combining them in laminar flows. Questions? Okay. We've seen this video on laminar flow earlier, so I'm not going to go over that again. So this slide is about modeling microfluidic laminar flows using equivalent circuits. So most of us have done some sort of circuit diagram analysis. You know, a typical circuit diagram, we draw some resistors, we draw some capacitors, and then we solve for the voltages and the currents at various nodes of the circuits. We can use things like Kirchhoff's current law and Kirchhoff's voltage law to do that. If you haven't done that, like I can help you do those types of analyses. It's they're quite intuitive to do. The reason we use circuit diagrams is because it makes the analysis easy, number one, and number two, it gives us intuition. After we've looked at some circuits before, like we start to get an intuition of how current is going to flow through the device. Similarly, a person who is designing microfluidic devices can model microfluidic channels using resistors, capacitors, voltage sources, and flow sources. And in doing that, they can get an intuition of how fluid is going to flow through the microfluidic channel. So I'll give you an example of this right now. So let's say this is what our microfluidic channel layout looks like. So we actually design our channels in a CAD program. We would draw the dimensions of what the channel will look like. This is what it looks like from the top view. So this is the width and the length of the channel. So we can build a network that looks like this. This is the inlet, and then this is the outlet. So the idea is that we will put in, we'll attach our source, probably like some sort of pump, to the inlet. We'll let the fluid flow through this network, and the outlet will be connected to some sort of waste container. So how do we model the flow through this channel network? Each one of these channels, as you recall, if we look from the previous slide here, each one of the channels can be thought of as a resistor. Just like we have V equals IR, in the fluidic domain we have delta P equals Q times RH, the hydraulic resistance. So each one of these channels can be considered a resistor. Now, in this one, you can think of this network as a series of channels that are connected together. So we have one channel here. We can think of this whole thing as another channel. This part is another channel, and so on. These different branches can be represented as resistors. So this part here we represent as R1. This branch up here we represent as R2. This branch down here, we also call this R2 because it has the same value. You can see that they're symmetric. And then we have the same value here as R1 at the outlet. So the way that this is represented, let me add another thing in here also. We have a flow source here, a current source. If you think about this in terms of the analogy, the current source represents, a source for those packets of fluid. Okay, just like a current source is delivering charge into the circuit, close this down. The current source is delivering fluid into the circuit. Right? A current source would represent a flow of liquid, like a pump, imagine a syringe pump, like where you're just pushing on a syringe and pushing liquid at a fixed flow rate through the channel. Can anyone tell me what a voltage source would be? If we were to put a voltage source in the circuit, what would that represent? Exactly. Yeah, that would be fixing the pressure at a certain point in the fluidic channel network. Okay. So if we were to analyze a circuit as an electrical circuit, we see that the current would flow through here. Then it would split up between these two branches. Half the current will end up going this way. Half the current will end up going this way. And then they meet back up here, and then they would go down here like so. Using Kirchhoff's current law or Kirchhoff's voltage law, we can solve for the voltage at this node, the voltage at this node. And those voltages actually would correspond to pressures at different points in the channel network. The pressure here is grounded, so you can consider this as atmospheric pressure. When you're flowing fluid through this channel, you're going to end up building a pressure difference across the channel. The pressure on this side is going to be larger than the pressure on this side. Think about it. You need pressure to push fluid through the network, right? So there's a certain, the pressure here would be 0, so that's represented by ground. Ground means 0 voltage, 0 pressure. You can solve for the voltage at this node. You can solve for the voltage at this node, and you can solve for the voltage at this node. You can figure out the pressures everywhere in your microfluidic network. Another piece of intuition, suppose that this channel were much thinner than this bottom channel here. Then this hydraulic resistance would be much larger than this one. In that case, the fluid flow through the upper channel would be less than the fluid flow through the bottom channel. So you would have an uneven spreading of the current. So less of the flow would go this way, more of the flow would go this way. Okay, that's, in circuits that would be called a current divider, but you can see the intuition in the microfluidic system as well. So once you have these circuits, it's very easy to model them as, these are called, circuit models are also called lumped element models. You can calculate the hydraulic resistances for each branch of your channel using this formula. Now this formula is giving the hydraulic resistance for a square or rectangular cross-section channel. The formula that we saw on this slide here, RH, this gives the hydraulic resistance for a circular cross-section channel. But as you'll see next week with our, with the fabrication demonstration, you'll see that indeed that in most cases the microfabricated channels have rectangular cross-sections. So you can use this formula to calculate the cross-section of a rectangular channel. Assumption also here is that the height is much less than the width, so it's a shallow channel. All right, so at the inlet, a constant input is represented by a current source. At the outlet, we assume a 0 pressure change. There are none shown in this example. There's only resistors shown in this example, but you could also represent a fluidic capacitance in there. If you had a chamber in there, a chamber that could expand or contract, for example, if you had a section of the channel with a membrane on top of it, then that membrane could expand and contract so that the chamber could become larger or smaller, like a balloon. Okay? And in that case, you could represent that as a fluidic capacitance. If your channel is made up of a flexible material, like a rubbery material that's not rigid, that can flex, if the channel itself can expand and contract, then that will also can be represented by a parasitic capacitance. Parasitic capacitance means a capacitance that's that you may not have intended for it to be there, but you have to model it because of the second order effects. So in the equivalent circuit, the voltage at each node represents the relative pressure, the current represents volumetric flow rates. Now in analyzing this circuit, again, if any of you need help with Kirchhoff's current law, Kirchhoff's voltage law, please do let me know. Using Kirchhoff's current law, the sum of all flows at each node is 0. So we can write an equation that says the current this way plus the current this way plus the current this way. The currents at all the nodes, at any one of the nodes, have to sum up to 0. By doing that now we can have a set of formulas at each one of these nodes. We solve. We have a set of equations and a set of unknowns. We can solve for the voltages or / the pressures at each one of these nodes. Let me get my. Yes. Yes, please.
I wonder, is the continuity equation still being effect in such a small scale?
I'm sorry?
Is the continuity equation still in effect in such a small scale?
The continuity equation. You mean the continuity equation for fluids?
Right.
So the continuity equation is a statement of conservation of mass.
Right.
Yes, that still holds at the microscale. Definitely.
In what scale, for example, micrometer or nanometer?
The conservation of mass, as far as I know, it holds at all length scales.
Actually, in such small scales, the mass conservation seems, for example, the assumption we used the Q, the particles, small particles, they are not continuous. So in such a small scale, maybe there are some spaces between each of the particles.
Oh, I see what you're getting at. Okay, remind your name again?
My name is Feng, F-E-N-G.
Feng. Okay. So Feng breaks up an interesting point here. He's like, at one point do these continuity models break down? Okay, I've been telling you that we model the fluid flow through a channel as we think about these small packets of fluid moving through the channel, right? Now, what's actually moving through the channel is molecules of water molecules, right? When you get down to this way of thinking about it, just as packets of fluid, assumes that all those packets are pretty much the same, right? That's fine at the micro-length scale. It's even fine at the nano-length scale. If you get down to the atomic scale, okay, if you're able to see this small, you'd see that there are actually a bunch of water molecules that are like sort of vibrating around each other. There's spaces between those water molecules, and they're flowing through this way, right? So in those cases, you're actually considering at the atomic level. That becomes a lot more tricky, right? If you want to solve systems at the atomic scale, where you're actually considering the movement of individual molecules, you have to use something called molecular dynamics simulations. Now, I don't know if you may have. Some of you may have heard about those. You can look this up online if you're interested. They are actually, a friend of mine, he actually does molecular dynamics simulations. They solve equations for actually the individual movement of molecules and how they interact with one another. The challenge with molecular dynamics simulations is that it takes a lot of computational power to solve an even small system, let's say like 40 atoms. It takes a lot of computational power to do that, right? You don't gain that much more intuition for these types of systems. In these types of systems, even at the nanoscale, you can start to analyze them using what's called continuum models. So that's the terminology that people use. Molecular models, like molecular dynamics models, are considering the individual atoms. Continuum models are analyzing these systems in terms of thinking about it in terms of small packets of fluid. Continuum models can use these things, partial differential equations, such as the Navier-Stokes equation, to model the phenomenon. Okay, everything that we're covering in this lecture they're all continuum models. Okay, but they do hold in microfluidic devices. They even hold in some nanoscale devices. That's a good question. Answer the. Okay. Yeah. All right. So next, dimensionless numbers in scaling analysis. The Reynolds number was one example of a dimensionless number, but there are many more. And in fact, this list is nowhere near complete. These are probably the most popular ones that are used in microscale analysis. Dimensionless numbers they're dimensionless, so they don't have any units. They typically represent the ratio of one force versus another force, or more generally, the ratio of one phenomena over another phenomena. They're often used in fluids and heat transfer to compare the relative importance of two competing phenomena, often expressed as a ratio of forces. In scaling analysis, we've been doing a lot of that in this module. We can use them to show the scaling of two phenomena in relation to one another. The Reynolds number, for example, is rho VL over mu. This is the ratio of inertial to viscous force. And as we saw, at low Reynolds number, the Navier-Stokes equation simplifies, and you end up getting these things called laminar flows. And the equations are very simple to analyze. You can model fluid flow through a network as just a simple set of a circuit diagram, and you can figure out the flow in each branch that way. The bond number is another example. This is the ratio of gravitational to surface tension force. Imagine a droplet. Okay, I work a lot with droplets, so I bring up these examples quite often. Imagine a droplet that is, I'll show you an example on another page. The droplet has a certain gravitational force. Right? A gravitational force would cause that droplet to fall down. The surface tension force is the force that keeps it circular. If you didn't have surface tension, the droplets would not appear spherical. We'll go over that on the next slide. But the bond number is, if you were to take a droplet and just put it on a surface, how circular that droplet looks is dependent on the bond number. If you have a lot of gravitational force, then the water will be a puddle. Right? If the ratio of gravitational to surface tension forces is large, it'll be like a puddle. At lower bond numbers, then the droplet will appear more like a sphere, more like a ball. One that's often used in microfluidic devices is the capillary number, the ratio of viscous to surface tension forces. Surface tension forces actually become quite significant at the microscale. So if you have a bubble inside your device, for example, that bubble, the surface tension of that bubble can actually kill your device. It makes it impossible to push fluid through there. There's something called a Laplace pressure that develops, and bubbles in microfluidic devices can be quite problematic. You don't want to get bubbles in your channel, usually. This is partially because the ratio of viscous and pressure forces to surface tension forces, the surface tension forces basically become more significant. If you have a droplet or a bubble flowing through a channel, the ratio of viscous forces to surface tension forces on that bubble is given by the capillary number. More examples here, the Grashof number, the ratio of buoyancy force to viscous force. Buoyancy forces become less significant at the microscale because, well, you tell me, what is buoyancy force dependent on? Is it L squared, or L cubed? L cubed, right. It's a mass-dependent phenomenon, right? The Weber number, the ratio of inertial to surface tension forces. The Peclet number, this is one we'll talk about in the microfluidics module. The ratio of advective to diffusive transport. When we're analyzing laminar flows like this, we use two dimensionless numbers to describe this phenomenon. One is the Reynolds number, the other one is a Peclet number. Okay, the Peclet number gives the ratio of advective to diffusive transport. So let's look at quickly what that means. Let's say you have, this stream here has an organic dye in it, which is causing it to appear light blue. Those molecules are being pushed by the liquid, right? Since the liquid is moving, the molecules are moving with the liquid. That's advection. Now the molecules, once they get here, you can see that there's a high concentration of these molecules at the top of the channel, lower concentration at the bottom of the channel. So what's going to happen? in terms of diffusion? Like which way are they going to diffuse? Down the concentration gradient, right? Eventually these molecules will start diffusing down. So when we talk about this type of system, we're talking about the ratio of advection to diffusion. Advection is what pushes the molecules this way. Diffusion is what causes the molecules to go down this way. So the Peclet number can be used to analyze how long will we be able to maintain this sort of like discontinuity in the different molecules before they start to mix together. So if you want to, we'll talk more about this in the next module. The Fourier number is the ratio of heat conduction rate to heat storage rate. That scales as 1 over length squared. Now this is an example we're going to actually look at next. Some things about like surface tension. Okay, I include this in here because I do a lot of work at surface tension. So there's my bias. But it's a nice example of showing the scaling of forces. Surface tension is due to the intermolecular cohesive forces which are stronger at the surface of the liquid compared to the bulk liquid. So this is what water looks like at the molecular level. So we were just talking about this. So the water molecules have some space between them. They have intermolecular forces which bring them together, which cause the water molecules to stay water. Now, more significant than that is that the water molecules at the edge. Okay. The intermolecular forces of the water molecules at the edge are stronger than the intermolecular forces than the water at the bulk. As a result, this forms what's called a tensile skin over the surface of the water. So this is what causes the water droplet to stay together as a droplet rather than breaking up. So this skin actually is sort of, you can think about it as a membrane. You can even put weight on that membrane before that membrane breaks if you put something light on there. This is an example of a bug, water strider, that is light enough that it can sit on water without falling in, without submerging. If I tried the same thing, I couldn't do that. This phenomena we can think about in terms of the bond number. The gravitational force is what's going to cause this object to sink into the water. The surface tension force, you can analyze the surface tension force this way. The surface tension force is trying to keep this membrane together and not allow this thing to fall in. So we mentioned the bond number is a ratio between the two, so you can nicely analyze these types of systems in terms of the bond number. The bond number, if we look at the gravity force, this is sort of a derivation of the bond number. The gravity force, the weight of the object is the mass of the object times the acceleration. Force equals ma. So the weight of the object is going to be the density times length cubed, so that's the mass of the object, multiplied by the gravitational constant, 9.8 meters per second squared. That's the gravity force. The surface tension force is given by sigma times L. Sigma is the surface tension. It scales as length. It's given in terms of newtons per meter. If you want to find the full surface tension force, you have to integrate the surface tension force over length, or multiply by a typical length scale. All right, so that's where the sigma L comes from. You have L cubed at the top, L at the bottom, so the bond number becomes proportional to L squared. So the bond number, as you go to the small scale, it very drastically drops. And this is why you can have an object like a water strider be able to sit on the surface of water, but I can't. Another example is a paper clip here. At the nanoscale, the surface tension effects become very, very significant. All right. So this is an example of the scaling of surface tension forces. It's given by the bond number. Microdroplets, a little bit more on surface tension. The surface tension forces form a skin which holds a droplet in a spherical shape. How tightly how tightly it's held creates a pressure difference between the inside and the outside of the drop. Okay, so you imagine that you have a drop like this, and you have the surface tension forces are forming a skin on the surface of the droplet. That skin, you can think about it like a balloon, right? The more tension is on the surface of the balloon, the more air pressure is going to be inside of it, right? Because that tension is really packing the air molecules together inside the balloon. This is described by the Laplace pressure, the pressure difference on the inside versus the outside. Delta P is equal to P outside, pressure out here, minus the pressure inside. It's given by 2 sigma divided by r. Sigma is the interfacial tension, or surface tension, and r is the radius of the drop. So this is interesting. This is a geometric dimension. This is telling us that when the r becomes small, the Laplace pressure shoots up. This is a 1 over x function, 1 over L function. So in microdroplets, interestingly, the Laplace pressure can approach 1 atmosphere, 15 psi. That's very significant. 1 atmosphere difference between the inside and outside of the drop. Okay, so this is one of the reasons why if you want to form like really small droplets, you actually have to use a surfactant to reduce some of the interfacial tension, or else it just won't be, the system won't be stable. A little bit more, like this is the bond number, the ratio of gravitational to surface tension force. You know, if you have a small droplet, then the gravitational force versus the surface tension force is small. So the surface tension force tries to keep the droplet spherical. Okay, without going into more details than that, we'll just say that the surface tension force, since this is exerting a force on the sphere, it actually tries to pack it in the form of a circle, which is the smallest surface area. The gravitational force will want the droplet to deform into a puddle, right? If you have a droplet sitting on a surface. Surface tension force will try to keep it spherical. The gravitational force will try to make it into a puddle. So the bond number describes, you know, at low bond number, you end up getting drops that look like this. At larger bond numbers, you end up getting puddles. Let's get this example here. This is a video from a very active researcher in the microfluidics field. He does some really nice work on the physics of flow, and he's also has a lot of nice work in droplet-based microfluidics. So you see how the droplet, it bounces. There's a few different dimensionless numbers at play here. First of all is the gravitational, the ratio of gravitational to surface tension forces. So what happens here is the droplet, I'll get into that in a second, the droplet bounces, but then it literally recollects itself, and it stays together, deforms a little bit, and eventually it settles on the surface here. What are the different forces at work here? You have surface tension. So surface tension is what's trying to keep the droplet together. You have gravitational forces, which is causing the droplet to drop. You have inertial forces. Inertial forces means like whichever direction a piece of fluid is going, it wants to continue in that direction. So in this type of system, we have the bond number, the ratio of gravitational to surface tension force. We also have the Weber number, the ratio of inertial to surface tension force. In both cases, the bond number and the Weber number are small enough they're small enough such that the surface tension forces they're significant enough that the surface tension forces can hold the droplet together. All right, if you did this at a larger scale, obviously the droplet would break up. You can find out, if you look through the internet, you can find all sorts of great videos on these sort of phenomena. You could spend days looking at them. So surface tension is so significant at the microscale, so why not use that as a pumping mechanism? This is an example of electrowetting. This is a technique that can be used to move droplets around. Hopefully this video will work. Oh, this one will not work. I think this one will. Let's try the YouTube videos. This is an example of electrowetting. You see how the shape of the droplet is changing? We'll talk more about electrowetting later, but what it does is that there's an array of electrodes on the surface. When you apply a voltage to these electrodes, so the voltage of the surface relative to the droplet itself is different. This actually causes the contact angle. It's a surface tension based phenomenon. It causes the contact angle to change. When that contact angle changes, you can cause the droplet to move in a certain direction. For example, if this electrode is actuated, the contact angle here will be less than the contact angle here, and the droplet will literally move from this grid to this grid, this electrode to this electrode. The surface tension forces drag the rest of the droplet with it. All right, we'll look at more at electrowetting later, but it's basically a way to control surface tension and contact angle using electric fields. When we apply a voltage to this electrode, we're reducing the contact angle there, and that's what causes the droplet to move from one place to another. The video that you just saw was an example of where we're changing let's watch it again. We're changing the voltage on the surface, and so that's changing the contact angle here. And because the surface tension effects are so significant, it can actually cause the droplet to change shape and move. So let's see another example here of that. So here we actually have one wire here. Let's watch that again. We have one wire at the top that's going into the bubble, and then we have let me rephrase that. There's a wire going into the bubble, and then there's the surface. Okay, you're applying a voltage between the wire and the surface below the droplet. When you apply the voltage, you can see that the shape of the drop changes. This is an example of an electrowetting system in action where you actually have a grid of electrodes. This is a video from Aaron Wheeler's group at the University of Toronto. He does a lot of nice work with electrowetting based systems. So you can see how electrowetting can be used to move around small pieces of fluid, mix them around, dispensing, mixing, merging, splitting, all the operations that you would do on a laboratory benchtop, you can do with these electrowetting systems. There's recently a company, a group who did some of the early work in electrowetting was out of Duke University, Richard Fair's group at Duke. They did some of the early work on electrowetting based systems, and they started a company called Advanced Liquid Logic. Advanced Liquid Logic was in operation for a long time. At one point, people thought that they just have a cool technology, but there's no real great applications. Well, recently they got bought out by Illumina for more than 100, well, for an undisclosed sum. And my guess is probably in the tens of millions or more. So Illumina is a company that does DNA sequencing. So this technology is actually being incorporated into the state-of-the-art DNA sequencers. So electrowetting phenomena, very cool, very, very cool. Lots of fluid operations you can do with that. This is some work that I did when I was a grad student. that uses surface tension. I guess the links aren't working right now. I'll describe this to you, and we can show you my website where I have these videos up there. Surface tension-based phenomena can be exploited for microscale fluid manipulation. Electrowetting was another example of that. For example, in our previous work, localized heats generate surface tension gradients creating Marangoni flow. These flows can be used to collect particles and droplets and manipulate liquids. In this case, what we did is we heated up the liquid. When you heat up the liquid, you reduce the surface tension locally. So when you create a surface tension gradient on the surface between air and oil, you actually create these flows on the surface. Okay, so this by applying a temperature gradient, you've actually created a pump. All right, this media says media not found. Okay. So let's just go to our website. Some videos on Marangoni flows here. So this is a grid of electrodes. Let's just watch this one. By activating the different, let's watch that again. This is a grid of microheaters. Okay, so by activating the different heaters, we can create temperature gradients on the surface, and by doing that, we can actually control the flow of objects. In this case, we were causing droplets to move in the fluid. And this is another example where we use these Marangoni flow patterns to collect. So this is a heat source. We can actually use them to collect particles in the flow, kind of like a vacuum cleaner, and then release them. Okay, so surface tension can be used as a pumping mechanism at the microscale. Let's turn this off. All right, so let's move on to the thermal domain now. Does anyone want a breather, or should we just continue? We're good? All right, so moving on to the thermal domain. In the thermal domain, the concepts that we're often interested in is temperature, heat flux, surface heat flux, and heat sources. Okay, and we're often interested in the flow of heat from one place to another. Relevant material properties include the thermal conductivity, the specific heat of a material, thermal diffusivity, the density of a material, and so on. More essential physics concepts, you can go here. These are concepts related to the thermal domain. Let's give it a second while that loads up. A heat sink is where the, okay, there we go. Heat and thermodynamics here. So, a lot of the things that we're going to be looking at here is things like specific heat, temperature, the conduction and convection of heat, and so on. So this is an example of a typical problem that we could analyze. The flow of heat from one place to another. Just like the flow of electricity from flow of charge from one place to another, heat flows from hot to cold. That's a very basic concept in heat conduction. Just like voltage, the charge flows from high to low voltage. So this diagram is showing an example. This is from, I believe it's Ellis Meng's book. I should have included that in here. Heat flowing from a hot temperature to a lower temperature, and that has a certain cross-sectional area. All right, the larger this cross-sectional area is, the more heat is going to flow between the two areas. The analytical equation in this case, we have the conservation of heat. dq dt times the gradient of the surface heat flux is equal to PS, which is the if you have any heat sources in there. If you don't have any heat sources, then this part drops out and you're just left with these two terms. Okay, so these equations are, they're similar and analogous to the relevant equations in the fluid and the electrical domain. Heat capacity is an important concept. This has to do with the thermal capacitance and the rate at which temperature changes. In electronics, we have this relation I equals C dV dt. Okay, so in a capacitor, you're dumping charge into that capacitor, and that changes the voltage across the capacitor. We'll see an example of the same thing with heat, where you have a thermal heat capacity. This has to do with the fact that objects hold heat. If I'm at a certain temperature, then it's going to take a certain amount of energy to bring me up to a higher temperature. And you're going to have to take a lot of energy away if you want to cool my temperature down. I'm made up mostly of water, so water has a certain heat capacity associated with it. Right. So we'll talk a little bit more about that. The Fourier's law of heat conduction, this is the transfer of heat from hot to cold. That's what I was just describing. This is described by Fourier's law. And then we have the heat equation here. This is sort of like a statement of conservation of heat, and it's used to analyze most heat transfer problems. Okay, in certain cases, there's some simplifying assumptions. For example, if you are at steady state, then this term goes to 0. If the temperature in the system is not changing, you just want to find steady state temperatures, this term goes to 0. If there are no heat sources in the system, then this term goes to 0. This term describes the conduction of heat from one place to another. So let's look at an example and we can revisit some of these things. Now we can talk about this in terms of the scaling advantage. At the microscale, we get fast heat transfer from one place to another. Why does this happen? We can look at this simple argument. Suppose we have an object, okay? That object has a certain amount of, it's at a certain temperature, and let's say it's at a higher temperature than its surroundings. The question we want to ask is, how fast does that object cool down? Right? And we've all had experience with this, right? If you heat up a big pot of water in the microwave, it takes a long time for that thing to cool down. But if you just have a teeny tiny, like just a little bit of water left, and you heat that up, that's going to cool down relatively quickly. Why does that happen? How does that scale? Heat flux has to do with surface area divided by the length. Okay, Fourier's law of heat conduction says that the more surface area you have, the more heat transfer you're going to get. And let me draw it out. So this object is radiating heat in all directions. Assume that's at some distance away from the object. This is at room temperature. So this is, we can call this T0. This object, we can call it T1. This is the hot object. At some distance away, L, you're at room temperature. Okay, and then this also has a geometric distance associated. There's a radius. This object has a certain dimension. Right? So if we scale down the entire system here, let me first say that the heat conduction say the heat flux. Alright, this is sort of a pain to use. It's proportional to the length divided by the surface area. So in the surface area, it has to do with r squared. Okay. So the closer this room temperature object is to the heated object, the more heat flux you're going to have. The more surface area you have here, the more the heat is going to flow between the two. So the heat flux, the surface area divided by the length, so this comes out to L. This scales as L. The heat capacity scales with the volume of the object, so that's length cubed. The more massive an object is, the heat capacity has to is the mass of the object multiplied by the specific heat. The specific heat is a material property. The mass of the object is whatever the mass of the object is. So that's coming back to this concept here. Okay, the heat capacity of an object is the specific heat multiplied by the density multiplied by the mass of the object. So let me write that down. I don't think it's in the notes here. Heat capacity. It's the ability of an object to retain heat. So whatever this object's heat capacity equals the mass times the density times the specific heat. We call that Cp. All right, if we look at the units for this, this is kilograms. Oh, sorry. So the mass. All right, and the heat capacity is the joules per kilogram times Kelvin. All right, so the heat capacity is joules per Kelvin. Okay. Now, what does this mean? Joules per Kelvin. It means how much energy, how many joules of energy do we have to put into that object in order to change the temperature by 1 Kelvin? Okay. Something with a lot of heat capacity means we have to dump a lot of heat energy into it just to change it by 1 degree. Now, heat capacity scales as m, so that is proportional to length cubed. So that heat capacity has to do with how quickly or how much energy has to leave this object before it reduces its temperature. Joules per Kelvin. All right, so the Fourier number gives the ratio of the heat conduction rate divided by the heat storage rate. And so this L over L cubed, so you end up getting this L squared term at the bottom. So at small length scale, the Fourier number goes up. So the heat conduction becomes more significant than the heat storage. What that means is that things can heat up and cool down very rapidly at the microscale. As a result, at the microscale, devices can be rapidly heated and cooled. This enables fast thermal sensors and actually improves heat removal in microprocessors. So I'll give you two examples here. This is a hot wire anemometer flow sensor that was published in 1997. Some of this work has been done, some of these work in thermal sensors has been done quite earlier. How a hot wire anemometer sensor works, it's a way to measure flow, by the way. It's a way to measure gas flow. You have two wires that are each heated. Let's say this one is heated and this one is not. This one is heated and this one can be used as a temperature sensor. Now, when you have flow this way, heat energy is being advected from this heated element to this element, which is the sensor. So at high flow rates, you're going to end up having, you're going to sense a temperature here, and at lower flow rates, you won't receive as much. Now, another way that these anemometers things work is that you look at the heat loss from a single element. If you just have a single wire floating around in the solution, now the flow rate is going to advect heat away from there. So if you could heat up this element and simultaneously measure the temperature of the element, then that's a way for you can correlate that with flow. Because the more flow there's going to be, the cooler this element is going to be. That's another type of sensor. There's a third type of sensor which is called time of flight, where this is heated up. You have a pulse of heat that's applied to this element, and that pulse of heat, if there's a flow, that pulse of heat will actually travel down this way in the flow, and then it'll be detected by this element. So there's a few different types of thermal sensors. Now, one of the advantages at the microscale is that these sensors work relatively fast. You can get a quick time response with them. So if you have quickly changing flow rates, you can measure that. Second example here, microchannel-based heat exchangers for cooling. I mentioned that microprocessor cooling is becoming a huge problem. The amount of heat that's generated in microprocessors is becoming very significant. So the problem is, how can we cool them down? One way that's been proposed is the concept of having microchannels inside, or microchannels right below the microprocessor. So let's say this was the microprocessor up here. Underneath there you have a series of microchannels where fluid is flowing through here. Surface area to volume ratio is large. This Fourier number, heat conduction to heat storage rate. At the small scale you get a lot of heat conduction, so you can dissipate heat more rapidly than you can at the macro scale. So by putting a series of channels in here, they were able to cool down the microprocessor. This is a very good example of why, how the scaling of thermal microsystems and why that's useful. This is called a microbolometer. Have any of you heard of these things before? Okay, are we familiar with night vision? You see night vision cameras used by the military? Let's zoom in here, like you see here on the right. The military uses these types of things, and security cameras use these types of things to look at, to get night vision. Night vision is based on temperature. You're looking at the temperature of objects rather than the light reflected off them. Okay. Objects emit heat, and so if you can detect that. Now, how can you make these type of devices? You actually have to essentially create a thermal image. This is a more detailed thermal image of someone's face. You can see the temperature gradients on their face. So essentially what you're doing here is you're creating an image of an object. You're looking at the temperature profile of the object. Okay, these instruments are actually quite useful for scientific purposes, and in night vision they're used for military and security type applications. The way that these are detected is by using what's called a microbolometer array. Basically an array of temperature sensors. Texas Instruments, we talked about the micromirror array, right? Each one of those elements was a single mirror. In the case of a microbolometer array, each one of these elements is a temperature detector, a heat detector. And you can have a huge array of these microbolometer elements to create a thermal image. This is an example of a device from FLIR Systems. They're one of the leaders in infrared cameras and thermal imagers. So a microbolometer is a thermally isolated structure coated with IR absorbing material, infrared absorbing material. When exposed to infrared, the island heats up. The temperature change is measured by an electronic circuit located underneath the pixel. So we look at this diagram here. The infrared energy is coming from here. It hits this microbolometer element. The microbolometer element is coated with some type of paint or some type of material that absorbs infrared radiation. And when it absorbs it, it heats it up. Okay, when this thing heats up, it creates a temperature change. So the temperature increases here, and that temperature change can actually be measured by an element right underneath there. This is a monolithic bipolar transistor. Transistors can be used to measure temperature change. They can also be used as the switching elements. Okay, you actually have a circuit underneath here which can interpret the data from each one of the pixels. So you actually have to have transistors which act as switching elements. Now, the way that you can measure temperature, one way that you can do it is by just looking at the resistance of this bolometer element. Okay, resistance changes with temperature, so the resistance of this element would change if it was made up of a resistive material. Another way you can do it is by having a temperature sensing element underneath here. Okay, you can create, you can use a transistor, for example, as a temperature sensing element and just detect the temperature change underneath the pixel. So scaling advantages in this case, there's two of them: thermal isolation and speed. The thermal resistance of this element, what we want is we want if infrared radiation is coming down here, we want this element to heat up. We want a significant temperature change, and we want that temperature change to be rapid. We want it to happen quickly. Why would we want it to happen rapidly? How would that help the performance of the camera if that temperature change happened rapidly? So we have infrared radiation coming in here to the microbolometer element. Why would we want this thing? Why would we want the temperature to change rapidly? And you can think about it less in terms of the physics. Think about it in terms of application. Good?
You can have a higher frame rate. You can actually scan an image and not have everything sort of blurred together.
Exactly. You can have a higher frame rate. You know, for those of you who take pictures with your cell phone cameras, you know, like you can take movies at 10 frames per second. You can take pictures at 30 frames per second, right? The faster your detection element responds, the faster your camera is, the faster the frame rate. So one of the scaling advantages is that your bolometer element becomes faster at the when you make them smaller. And the other advantage, of course, is that you can have a huge array of them in just a small area. Another advantage is the thermal isolation. Like you have very tiny legs here, so the amount of heat that's conducted through these legs into the substrate is less. So even with a small amount of infrared radiation, you can get it to increase in temperature significantly, enough where you can detect it. So thermal isolation and speed is the advantages of the microbolometer. This is how we can model a microbolometer. It's an important parameter of an IR detector is its frame rate, its speed. We can use equivalent circuits to model how long it takes for the bolometer to heat up. So imagine that we have a membrane here, and that membrane is coated with that infrared absorbing material, and then it's connected to the substrate. So let's draw a simplified diagram of the system. This is the bolometer element. And this bolometer element is connected through these legs to a substrate. Now, this is a good example of analysis in thermal systems, okay? In electrical systems, we say this part is at this voltage, this is the current here, and so on. In thermal systems, we can also do a similar analysis. We say, just like in electrical systems, we'd say this is ground. We can say that this is thermal ground. So this is T equals 0. We can call this T1. That's the temperature that we're interested in. we want to know, the question we're trying to answer is how fast does this bolometer heat up and cool down? We want a camera with a fast frame rate. So in this system, this is a simple heat conduction example. You have a heat source, you have radiation coming in from the top, so this is generating heat. The bolometer is generating heat, and then heat is also flowing from the bolometer down the legs this way and then down the legs this way. Right? Heat flows through heat conductive materials. If this bolometer was connected to the substrate through some legs, of course you need some legs to hold it up, right? Then heat is going to be primarily conducted through those legs into the substrate. The substrate is the chip that it's sitting on, and we make the simplifying assumption that the chip is at T equals 0. Now T equals 0 doesn't mean 0 Kelvin. It doesn't mean absolute 0. It means the relative temperature is 0. Okay, so T1 will be the temperature difference between this and the substrate. All right, so we have the bolometer. The bolometer is generating heat. The heat is flowing through the legs into the substrate. Now the way that we can model this is we can start off with a current source. In the thermal domain, we're concerned with the flow of heat. In the thermal domain, a current source represents heat generation. We're creating heat. Okay, in the electrical domain of current sources is generating charge, right? It's pushing charge into the system. In the thermal domain, the unit element is heat. We're pushing heat into the system. So this heat generating element here, the fact that the bolometer is heating up, that can be represented by a current source, which represents, so we say, heat source. So this is the bolometer. Now, in thermal circuit modeling, we're modeling heat conduction. So, we look at the different paths that the heat can flow. There's one leg over on the left side, there's one leg over on the right side. So we can put two different resistances, and those are what's called thermal resistances, RTH. We can calculate the thermal resistances. I showed you a formula for that several slides earlier. It's RTH is equal to, this is in your notes too, the length of the leg divided by the thermal conductivity times the cross-sectional area. The wider the legs are, the more cross-sectional area you have, the more room for heat to move through it, the more heat is conducted through there. This is very similar to the equation for the resistance of a wire. So we have heat being generated in the wire. The heat is just like just like the current flows through this resistor, it creates a delta T. If current flows through a resistor, it creates delta V. Current flowing through these thermal resistors creates a delta T. So this is T1. The voltage at this node is equal to T1. If we solve for the circuit, we can solve for what the temperature is if we know what the thermal resistances are. The higher the thermal resistance, the more thermally isolated the device is. We have to add another element here in here. We're adding a capacitor in here. This is C. The thermal capacitance. Now, why do we add a thermal capacitance in there? Thermal capacitance is an energy storage element. Voltage cannot change instantaneously across a capacitor. Similarly, in the thermal domain, the temperature of this cannot change instantaneously. I'll repeat that. In the electrical domain, there's this principle that the voltage across a capacitor cannot change instantaneously. Similarly, in the thermal domain, the temperature of this element cannot change instantaneously. Instead, the temperature change is proportional to how quickly heat is flowing away from it. In the electrical domain, the charge across a capacitor is proportional. How quickly the charge changes depends on how much current is flowing away from the capacitor. So this is how we model the circuit domain. We have a temperature at this node, so T1, similar to how we have voltage across a capacitor. Now, we can charge or discharge this capacitor, and in the thermal domain, what that means is we can heat up or cool down the object. So the thermal capacitance of this object, it has to do with the heat capacity. So that has to do with this thing here that we looked at earlier. Now, the specific formula for the thermal capacitance we can find using just this concept of specific heat. It's joules per Kelvin. Oops. Let's go back to this. You have the bolometer element, we have the thermal capacitance, and we have these two thermal resistances. So this is our equivalent circuit model. Okay, capacitance and two resistances. The IR radiation generates heat, which can be modeled by a current source. The pixel itself has a thermal capacity because it takes energy to heat and cool it. This is modeled by a capacitor. Heat can travel through each leg to the thermally grounded substrate. We model this by a resistor. Notice we're actually neglecting the heat transfer through the air. You can actually have a little bit of heat transfer through the air. Now, this is a thermal parallel RC circuit. How many of you are familiar with RC circuits? Have seen them before? Resistor capacitor circuits, a low-pass filter. Hopefully some of you. Okay, how many of you have taken Circuits 1? Not here or from your circuits class, do you remember when you do low-pass filters? Low-pass filters consist of a resistor and capacitor. Resistor and capacitor circuits. Okay, well, an RC circuit consists of a circuit that has resistors in it and capacitors in it. Now, a fundamental property of an RC circuit is that the capacitance of the circuit cannot change. I'm sorry. The voltage across the circuit cannot change instantaneously. In the thermal domain, what that means is that the temperature across the capacitor can't change instantaneously. The characteristic time it takes to change the temperature by 70 to 80% is this time constant tau. So tau is equal to R times C. All right, the equivalent resistance in this circuit, you have these two resistors that are in parallel with one another. So this is the two resistors in parallel. The equivalent resistance is 1/2 RTH. And then this is multiplied by the capacitance in the circuit, which is CTH. So the thermal time constant of the detector is given by this simple equation. If you have not seen RC circuits before, for those of you who are not from electrical engineering, it's okay. Wikipedia and there's other few online sources that has like great, they're great resources for learning just learning a basic concept very quickly, and it's described in nice terms. So just go and do that. I recommend that you do so that you can understand this example. Basically, what this means is that this time constant, using this equivalent circuit model, you can calculate how quickly the bolometer will respond, how much time it takes for it to heat up and cool down. Okay, and obviously we're interested in that because if we want to make a thermal imager, we would like that thermal imager to respond rapidly. So a little bit more about this domain. In the equivalent circuit model, RTH represents thermal resistances. The current source represents heat being generated. The voltage at each one of the nodes of the circuit corresponds to a corresponding temperature. Temperature T. Right, so in solving this circuit, we're doing two things. First of all, we're finding out if you have a certain amount of heat generated, what is the temperature of this node. And the second thing we can do to analyze this is by looking at the resistances and the capacitances, we can look at how quickly the temperature at this node will change. In other words, how quickly the thing can be heated up and cooled down. If you need any additional help with like RC circuits, I'm happy to help give you an additional tutorial on that. But does this sort of make sense? This is equivalent circuit modeling. We're almost out of time here, so let's see if we can finish up these 2 slides. The scaling advantage. In one of the scaling advantages was the fact that you have fast heat transfer and things can heat up and cool down very rapidly. Another scaling advantage is that you have temperature gradients. I've shown you these examples of some of the work I did previously on using surface tension as a pump. This phenomenon is called Marangoni flow. So if you heat up a portion of the surface of the liquid, you locally reduce the surface tension. Now, the way this works is actually through a temperature gradient. At the microscale, you can get substantial temperature gradients. The temperature gradient is dT dx, the change in temperature with respect to a certain distance. So at the microscale, it's possible to get something very hot here and something very cold next to it. So in this case, what we're doing is we're heating up the surface of the liquid, and just a little bit further away, the surface is at room temperature. So we can get a very sharp temperature gradient across the surface of the liquid. Surface tension is proportional to, or is inversely related with the temperature of the surface. So we can get a very sharp surface tension gradient here, and that actually generates flow. Okay, and these flows I showed you earlier, if you can control these flows and use them to do various types of collection and fluid manipulations. So this is more of an example of how temperature gradients can be exploited at the microscale. This is a slide from Steven Centuria's textbook, which brings up an important point with the thermal domain. A lot of energy from other domains is dissipated into the thermal domain. Okay, for example, in mechanics, if you have friction for an object, the friction is converted to heat. In the electrical domain, if you heat up a resistor, if you run current through a resistor, you're generating heat. In the magnetic domain, you can get eddy currents. In fluids, you have viscous dissipation, that generates heat. In the chemical domain, diffusions and reactions can also generate heat. So the thermal domain is unique in the sense that other domains dump energy into the thermal domain. So this is shown in this schematic here. Now, as a result of that, you can actually use equivalent circuit modeling to sort of show that. This is an example, for example, if you have in a hot wire anemometer, this example that I showed you earlier, this tiny element is heated up by running a current through it. It's Joule heating. Imagine just a wire, and we're running current through there, we're heating it up. And this heat is being generated in the wire, and then as the heat is being generated, the heat is also dissipated. Some of the heat travels through this leg back through here, some of it is radiated out into the air, and so on. Right? So this is a two-domain problem, multi-domain problem. This can be modeled by a circuit that includes elements from the electrical domain as well as the thermal domain. So this is an electric circuit here. So you have a voltage source, a resistor, and a current running through there. So this is representing your electrical circuit. On the right side, you have a thermal circuit, and you have this dotted line that shows that they're coupled together. The thermal circuit shows a current source. The current source is V squared over R. This is the power generated by the resistor. The power generated by the resistor is the amount of power that's being converted to heat. This represents Joule heating. This thermal energy is going through this circuit. This is the thermal capacitance of that device, the wire that's being heated. And this is the thermal resistance. This represents the conduction, the paths of heat conduction when heat is being generated in the anemometer, where does the heat go? It goes through the substrate, it goes into the air. So this thermal resistance represents the paths for the heat to go once it's generated. So this is an example of a coupled circuit model for representing the energy transfer between two different domains. So it looks like we're out of time right now. So I would like to, we'll get into the mechanical domain next time, and then we'll wrap this up. Any questions about things that we covered today? Okay, so I threw a lot of different information at you from the different domains. If there's anything that you're confused about, please do feel free to go over the lecture notes again. Questions about circuit modeling, there are a lot of nice tutorials on doing circuit modeling or circuit analysis on on various online sources. So take a look at that. And finally, I will be posting a homework assignment on scaling. Just doing some basic analyses of scaling phenomena and modeling. I will be posting that sometime this weekend or early next week. Okay, and when I'll post it and also let you know what the due date is. Just some practice to help get you thinking about scaling laws and analysis in the different energy domains. Okay, all right. Thanks a lot for coming to the makeup session today. Next week we will have. I'll send out information about that, but Wednesday, plan to come to 3133 Engineering. Priyan will be giving a demonstration on how the different steps involved in making microfluidic devices. Look at your messages on Blackboard, because we'll post a link to a video from Stanford Microfluidics Foundry that talks. It's a video about the soft lithography process used to make microfluidic chips. Just watch that, and it'll give you a sense for how it's done, and then we'll just have a demo of that in the lab on Wednesday of next week. No class on Monday. All right? Thanks a lot. You have a good weekend.